All right. Oh.
Sorry, I'm just trying to make sure I have this right. So, I think it's so you got more. Yeah. I got like, I think it was like 31 for each piece. Yeah, so and it's basically is
All right. When you type in the 6.67, that's the negative 10. Right? Oh, yeah. So have you type it in?
It does, but we're not going to
And now it's negative. Typically, what I've seen students do is they, when they're off by a factor of 10, 6.67, and then they hit times 10, then hit EE, negative 11. And that introduces another 10 in the problem. So you don't type times 10 at all. And I don't know if that's what you did before. If you did it correctly that time.
What did I do this time?
You did 6.67 EE, negative 11. Yeah.
Okay.
Yeah, because the EE automatically has the times 10 to that, so you don't type that part.
Oh, okay. I think that's what I was looking for, yeah. Okay, thank you.
Yep. All right. So let's talk about our sun becoming a black hole. But first thing we need to do before we do that is, if we have some planet here, which I cleverly labeled X, and I'm going to launch something from the surface of the planet. The question is, how fast do I need to shoot something in order for it never to return? Now, part of this is that we assume that whatever I'm shooting is not actually going to hit anything. So there's no air resistance, there's no moon or planet, nothing else that's going to hit it. The nicely simplified problem of I'm launching something, how fast does it need to go so that it will not return? Because I think most people can experience, or at least appreciate the fact that if I throw the ball into the air, it will come back. If I throw it harder, it will eventually come back because I cannot get it up near that speed. This is done using conservation of energy. Yay. Once it is launched, what are the forces acting on the object? I have some object here. What are the forces acting on the object once I have launched it? And
Force from your hand launching your boat.
once it's launched,
Oh.
that's after the launch. My hand, I do not have Jedi powers. What's it touching? Normal force requires contact. This is just an object all by its lonesome being shot outwards. I was going along with weight. Yeah, the gravitational force. That's it. All right, so gravitational force, is that a conservative force or a non-conservative force? It's one of those two choices. It is indeed conservative. It's the main one that we dealt with up till now is conservative. All right, so energy is conserved. So whatever my energy is at launch, just after launch is the energy that I have the entire time. So we're just going to start out with my, whatever energy I start out with is the energy I've got at the end. No booster rockets either, by the way. All right, so once this thing has been launched, shot out with however fast it needs to go, we assume it's not going to explode. Don't have to worry about rest energy here. So what are the two types of energy I am worried about here? So whatever kinetic I have initially, plus whatever potential I have initially, it's gotta be the sum afterwards too. All right, so now we get to the formula stage. All of you know it, you've recited it, you've done it in unison. It's a beautiful thing. We will have one more moment of beauty here. What is the formula for kinetic energy? I'm not quite sure that all of that was so enthusiastic as well, beautiful, but it was good enough. So 1/2 mv initial squared. Now potential energy, now let's go through the routine. What's the formula for potential energy? Thank you. The one associated with the generalized gravitational formula, because mg doesn't quite work here because little g is changing as we go. This is the one that I just gave you the formula. It's minus big G mass of x, mass of object, this is mass of object, over R initial. So G mass 1 mass 2 divided by R negative. That's just the formula, and I'm just giving it to you. Deriving it requires calculus. So 1/2 mass of the object times the speed, final speed of the object squared minus G mx mo over R final. So all I've done is just kinetic plus potential beforehand is equal to kinetic plus potential afterwards. Now, if you're wondering why I have a minus there when I just said plus, because the formula for potential energy has a negative in there. I'm adding a negative.
What is X and O?
X stands for the planet X, and O stands for the object.
Okay.
Now, at this point, whenever, for most energy problems, you get to this point, you get to go, all right, what can we get rid of? I will tell you, we can get rid of some of this. What is equal to 0?
Is it the initial velocity?
No, because we're dealing with just after it's been launched. It's whatever, it's definitely not 0 just after launch.
Final velocity?
Yeah. Now, final velocity is never officially 0. We're going to get rid of that term, and I'm going to justify it, because we're physicists, not mathematicians. If it ever actually does stop, it's going to come back. So we want this thing to never come back, so it's going to keep going. However, that speed is going to get so incredibly tiny that it will be so close to 0 that we can ignore it. So this is 0 because the final speed is approximately 0. It's moving really slowly. But it's so far away from the planet that the acceleration isn't much, so it's not changing much by the time you get out there. All right, what's the other one that is going to be officially close enough to 0 to count for physicists?
Is there no other object other than what's being launched?
There's the planet and the object being launched. That's it.
I understand.
Gravity, because once you get out
Are you suggesting that this goes away?
I mean, I guess because the goal is to get it out of, so it doesn't return, which means we'd be getting it out of, so there's no final.
We're never getting out of the gravitational pull.
That's right.
We're just getting far enough away so that it is slowing us down so at such a rate that we never actually stop. So we'll think about that. If we are What is R, by the way? Okay, distance between what two objects?
Center, center to center,
I still didn't understand.
center to center. Center to center.
Man, I'm still having trouble. Are you hearing her?
She said center to center.
Oh, so, yes, yes.
Thank you.
Sorry, because I'm having hearing issues
Mm.
still. All right, it's center to center. So when this thing is really far away, what does that tell us about R sub F?
It's faster,
It's what?
faster. Oh,
Man.
they're faster.
Still waiting for the point where I get a hearing aid. I just feel like suddenly I get a hearing aid, everything, I can be able to hear people.
It's gonna get bigger, the radius?
Yeah, it gets bigger. This is the distance between the center to center. When that object gets really far away, this gets huge. So what do you know about fractions with a huge denominator?
I think it's smaller.
Like you mean it.
Smaller.
Yes. Take any fraction, because the numerator, big G is a constant, mass of the planet is a constant-ish, mass of the object is constant. This is some constant divided by a huge number. You know, whatever that is, just divide by an even bigger number, and then divide by an even bigger number. This fraction is going to get so incredibly tiny that it's close enough to zero. That's zero because R sub F goes to infinity, which means that 1 over R sub F goes to 0. So when this thing is far, far away, it's practically stopped, not stopped, but practically stopped, and the gravitational influence is minimal. Luis?
Is that bottom one VF squared under the equation?
That's VI squared there, VF squared there. Oh, here?
Yeah.
Oh, those are squiggles to indicate approximately.
Oh, okay.
So what we have done here, what we've basically started with the energy equation and we've reduced it down to the kinetic plus the potential initially is equal to 0. So all I'm going to do is I'm going to add this over to the other side. And so what I have is the kinetic energy, 1/2 mv mass of object times initial speed squared is equal to big G, mass of the planet, mass of the object over whatever that initial distance is. First off, mass of the object, factor on both sides, we can get rid of it. It cancels out. Right now I'm just trying to find the speed. So I'm going to solve for v here. So first I'm going to get rid of this 1/2. Just multiply both sides by 2. So my vi squared is equal to 2g mass of the planet over the initial distance here. This initial ri is just the radius of the planet. We launch from the surface. So this is the radius of x. So that initial speed to get rid of this thing, so this thing never returns, is the square root of 2 times the gravitational constant times the mass of the planet over the radius of the planet. So this is the formula for escape speed. Let's plug and chug. Let's find out what it is for Earth. What's the escape speed for Earth? Kimberly.
Why did you put 2? Right, what?
Why did I put 2 here?
Yeah, how did you get there?
Because I have a 1/2 on this side, and I'm trying to get this by itself.
Oh.
So I divide by 1/2 or multiply by 2 to get rid of this.
Oh.
Elaine?
Now where did the RS come from? Cause that's the RI.
R sub I is the initial distance between the object and the planet. And if I'm launching it from the surface, that distance is just the radius of the planet.
Oh, okay.
So R sub X is just the radius of the planet. Other questions at this point? see what the escape speed for Earth is. So that would be the square root of 2 times 6.67 times 10 to the negative 11 times the mass of our planet, 5.98 times 10 to the 24th, divided by the radius of our planet, which is 6.37 times 10 to the 6th. Someone's going to zip this out on the calculator and tell me what it is after I do this question. Brianna?
But, did you make the other two numbers up, other set of numbers up?
These numbers?
I know you got the 6.67.
Right.
Where'd you get the math?
I was doing this specifically for Earth. This is in general, whatever the planet happens to be, and now I'm doing it specifically for Earth. How fast do I need to shoot something off the surface of the Earth, assuming it doesn't hit any air, for it never to return?
That's the math of the Earth.
That's the mass of the Earth. In kilograms. So we have an answer?
Yeah, but I don't know. It's 125,232,653.
Did you get to do the square root?
Oh, yeah.
I got 11,119.739
Units?
newtons.
What do we find?
Wait,
Someone else could jump in, help me see, or just you enjoy watching or try to figure it out. It's I know it's a little bit more than 11,000, so I'm feeling comfortable with something around there. Units, we're still at the, what are the units?
Meters per second?
Yes. We found the speed. This is the escape speed. So if we can shoot an object, assuming it doesn't hit any air or anything like that, at a little over 11,000 meters a second, which is about 24,000 miles per hour, it will leave Earth and it will not return. Yeah, I'm not sure. Generally when I see that, someone misreads something. This is negative 11, 24, and a 6. Yeah, I'm not.
think my, so funny just doesn't hurt the function. You know what I mean?
Yeah, so. I'm not quite sure what you did. Or if you develop the physics attitude, you're right, everyone else is wrong. Just remember that. I can't believe these peasants came up with the same quote value. All right. The formula for escape speed, I think that's was a question. Yeah, question 9 deals with escape speed. But I promised you black holes, so we got to get there. Questions before I segue into black holes?
So that 5.98 is the mass of the Earth?
5.98 times 10 to the 24th
Yeah.
is the mass of the Earth.
Okay.
At least as of this morning. Now, the mass of the Earth actually does change. There are certain particles that will hit escape speed and then leave, but we're also going through various bits of, I'm going to get the language wrong because I can never remember meteors, meteorites, comets, and so forth. There's space dust out there that we go through, and we as a net result, we actually end up gaining mass. However, there is an ebb and flow. black holes. Now, it turns out that the speed of light in a vacuum is constant. And if you make that assumption, one of the implications of it is that time is not constant. Someone running, their time is going to be slower than someone who is standing still. Now, we don't notice it because we are all traveling so slowly compared to the speed of light that it really doesn't make any difference. GPS satellites, they actually do take that into account. They take in what's called special relativity, which deals with the speed of light being constant, and general relativity, which deals with the warping of space and time. And they take that into account. Otherwise, the GPS satellites would start being off by, I think it's 30 meters a day if it ignored that stuff. But the speed of light, turns out it's a maximum value. Or I should say, anything that starts out slower than the speed of light will never get to the speed of light, no matter what. In classical mechanics, in theory, I can apply a force, the object will accelerate. As it accelerates, it could eventually pass any speed that I want. But once you get into special relativity, the faster it goes, the more mass it is, and so the force has less effect and the acceleration drops off. And you'll get closer and closer to the speed of light, but never actually get to it. So if the speed of light is the maximum speed that I can ever launch this thing, the question is, at what point will it never escape? Assuming I actually go to the speed of light. So I have this equation right here. All I'm going to do is I'm going to flip across the diagonal, because I can turn anything into a fraction just by putting it over 1. I have two fractions equal to each other. I could cross multiply if I wanted to. I could swap things across the diagonal, still legitimate. So I'm basically going to swap the radius and the speed squared here. So that becomes Rx is equal